Here's the solution to problem number 16 from section 8.5. And again, we're looking for just a test to decide whether the series converges. And there really is more than one way to do a lot of these problems. But let's take it through the sort of basics here. When we see a function like this, one thing we were talking about is to kind of blur your eyes and look at the higher growth functions whenever there's terms being added or subtracted. And in this problem, we can see that in the denominator, we're adding k to the 11th power plus 3. And so surely that is pretty much just k to the 11th power when the k's are getting large. So let me make a note of that. So k to the 8th over k to the 11th plus 3 is comparable to k to the 8th over just k to the 11th. So that is comparable to is a term that they used early in the chapter on sequences to mean something very specific. It means that the ratio of those two expressions in the limit gets close to a finite number. So they're growing at the same speed. And that's really the basis of what we call the limit comparison test, is checking to make sure that comparability that we claim is there really is there by looking at the limit of the ratio of those two expressions. But the limit comparison test is sort of our last resort in some way, because it's the one test where even though we'll get a correct answer about convergence using the limit comparison test, we completely lose track of how fast the convergence might be happening and what the actual limit might be, like what the numerical value might be if we have a convergent series. So if we can use the comparison test, then we should try to use the comparison test if we're interested in getting an estimate for the values. So that's why in a lot of these problems, they'll give a preference for the comparison test instead of the limit comparison test, even though both are technically correct for determining convergence. So the reason here that the comparison test is easy is because these two expressions, k to the 8th over k to the 11th plus 3 and k to the 8th over k to the 11th, those expressions are identical except for the denominators, and the expression on the left has a larger denominator. So what we learned was larger denominator means smaller fraction. So I know for a fact that this is always true, that k to the 8th over k to the 11th plus 3 is actually less than k to the 8th over k to the 11th. So it's not just that it looks similar to it or grows like it when the k's are very large. It's actually less than k to the 8th over k to the 11th for every single value of k, even the small ones. And so that's a much stronger statement. And so that will give us a much stronger result. So let's go with that. And I'll say, since this is always true, that means that the series that I get around the first expression must be no bigger than the series I get using the second expression. And of course, the real advantage is that new thing on the right, this is the new expression, is actually equal to the series 1 over k cubed. And that's just by simplifying these powers of k. K to the 8th over k to the 11th is equal to 1 over k cubed. And this is a convergent p-series. So that's a p-series where the p is equal to 3. So the sum that I'm considering in this problem, this original series, is less than or equal to this guy, and this guy converges. So therefore, this has to converge. There's no way for this to be less than or equal to a finite number and not have this be a finite number. And so if all we cared about were convergence, then we'd be able to conclude this converges. And for this problem, that's definitely all we care about, is the issue about whether this series converges or not. But so we've checked that converges, and as far as this problem is concerned, we're done. So we could say by the comparison test, this series converges. It is not wrong to say by the limit comparison test. That's also completely true. And that would just be a matter of checking that the ratio, that this divided by this in the limit, when the k's are enormous, tends to a finite value. So taking that and dividing it by that and looking at the limit as k goes to infinity is all we'd have to do for the limit comparison test. But that means that these guys are comparable eventually when the k's are enormous. The comparison test actually tells us that that these guys are comparable to these guys right off the bat. And so that is a stronger result. The other thing that allows us to do is it allows us to get a bound on the size of this thing. So if we're trying to do any kind of error analysis for this, we'll be able to do that off of the comparison test, and we would not be able to do that off of the limit comparison test. For example, I can get a pretty good first guess at this because, let me add these are all 1 to infinity. Remember that we showed that that a series has to be no bigger than the corresponding integral. Every time we analyzed our p-series, we did it by comparing to an integral, and so this is one of the comparisons that we made. This is based on drawing the picture for the integral from 1 to infinity of 1 over x cubed, and then drawing left sums under it. Right sums under it. The right sums will fall underneath the curve. It's not strictly true, actually. It's really the going from 2 to infinity that will do that. But nevertheless, the point here is that there's a bound that I can actually compute, because this integral I can actually do the arithmetic on it, and this integral will end up being a half. So the sum of these guys starting at 2 and going forever is no more than a half. So the sum of these guys starting at 2 and going forever is no more than a half. So we immediately can get a bound on that. And then I can apply that same reasoning to those remainders. So I can say, suppose I sum the first 10 terms of this, what's left over? Well, that'll be this sum starting with 11, and I can compare that to an integral, and I can find out what that is as well. So all of that kind of estimates with error analysis we can do after we have shown convergence based on the comparison test, and we would not be able to do that if we found convergence based on the limit comparison test, because the limit comparison test just tells us these guys are similar eventually. Maybe after k is 1,000 or 1,000,000, they'll start being similar. But that's all the limit comparison test tells us, whereas the comparison test tells us that these guys are comparable at the very beginning as well. So bottom line is, on the homework especially, if you can do a comparison test, I think that's what it will prefer. But I'm still holding my breath to see what answers this thing accepts, because as I said in class, for a lot of these problems, there's more than one test that you can correctly do to determine convergence.